Okay, we have moved into Chapter 4, Applications of Derivatives. We're eventually trying to get to Section 4.5, which is about applied optimization problems, and that's really the meat of what we're getting to, probably one of the most important applications of derivatives. But before that, we need some preliminary material. So here in Section 4.1, we're talking about extrema of functions, and extrema means minimum or maximum. It's just extrema means in general talking about one of those or both of those. And then we're also learned the difference between absolute or sometimes called global extrema versus local extrema. So an absolute or global extrema means the absolutely biggest, absolutely maximum function value of a function over an entire interval, whatever interval we're talking about, or the absolute minimum would be the very smallest minimum value over an entire interval, as opposed to local minima, which would be, for example, pretending you're standing on a mountain range. You might be on a high point, some mountain where everything around you goes down, but there may be a mountain taller somewhere else that you can see where, so you're not at the absolute maximum. That's kind of the difference between local and global or absolute maxima versus and minima. So, please take a read through the notes, fill in the blanks, and make sure you understand all that. But I want to get to the examples here. So we're going to do all three examples 53, 54, and 55 in this video. All of these are about how to find the absolute extrema of a continuous function on a finite closed interval. So in other words, where we are including the endpoints of that interval. So, what you learned in going through the notes is that absolute extrema occur either at the endpoints of an interval, if we include the endpoints, so a closed interval, or they occur at critical points, right? A critical point is where the derivative is either equal to zero or does not exist. Those are called critical points. So if the derivative equals zero, that means we have a horizontal tangent line. So we have either an absolute max or an absolute min. Or we have a local max or a local min for sure, but we have a minimum or maximum value locally. And then if the derivative doesn't exist, that's also a point where you could have a maximum or a local max or a local minimum value in the sense of the could have a corner or something like that where the derivative doesn't exist. But we still have a continuous function, so we don't have to worry about it jumping out of the interval. Okay, so once we evaluate f at all the critical points and the endpoints, we just take the largest and the smallest of these values as the absolute maximum and the absolute minimum of the function on that interval. So in example 53, let's say we want to consider the function f of x equals x squared on the interval minus 2 to 1, including those endpoints, the closed interval minus 2 to 1. So first of all, we look for critical points that are on that interval. So we take the derivative. We get the derivative very easy, 2x. We set it equal to 0 because we know that 2x exists everywhere, so we don't have to worry about it not existing. Set it equal to 0. We get that x equals 0 is the only critical point. Now we look and make sure that's on our interval. Yes, it is. 0 is between minus 2 and 1, so that is on our interval. So all you do is you check the function value at the endpoints and that critical point. So at x equals minus 2, f of minus 2 would be minus 2 squared, which is 4. At x equals 0, f of 0 would be 0 squared, which is 0. And at x equals 1, f of 1 equals 1 squared, which is 1. So the absolute maximum value of the function on that interval is 4, which occurs at x equals minus 2. And the absolute minimum value of the function on that interval is 0, which occurs at x equals 0. Okay, let's do another, fairly simple one the same way. Same idea. We have a g of t equals 8t minus t to the fourth, and we're again on the interval minus 2 to 1. So I'm going to take the derivative of g. I get 8 minus 4t cubed. That exists everywhere, so I don't need to worry about it not existing. But I set it equal to 0, and I solve for t, and I get that t is equal to the cube root of 2. And that's bigger than 1. So notice that that critical point is not on the interval minus 2 to 1. We certainly don't consider critical points outside of our interval because we want the maximum minimum value of the function on that interval. So for this example, all we actually have to do is check the endpoints. So at t equals minus 2, g of minus 2 is equal to minus 32. And at t equals 1, g of 1 is equal to 7. So the absolute minimum value of the function is minus 32, which occurs at t equals minus 2, and the absolute maximum value of the function is 7, which occurs at t equals 1. Okay, and our last example in this section, example 55, we want to find the absolute maximum and minimum values of f of x equals x to the 2/3 on minus 2, 3. So now in this case, when I take the derivative of f prime of x, I get 2/3 x to the minus 1/3, which if I want to write it with root notation, I'd write it as 2 over 3 times the cube root of x. So this doesn't equal 0 anywhere, right? If you're going to set this equal to 0, you'd be basically asking where's the denominator, or excuse me, where's the numerator equal to 0? So 2 cannot be 0. So this does not equal 0 anywhere. However, we have a problem in that the derivative does not exist at x equals 0, right? So I look to see where the denominator is equal to 0 because that would be a problem. The derivative is undefined there. It doesn't exist there. Okay, so x equals 0 then is a critical point. Make sure it's on the interval. The interval is minus 2 to 3, so yes, that is on my interval. So then the next thing I do is I go ahead and I check the endpoints and the critical point. At x equals minus 2, the function value is the cube root of 4. At x equals 0, the function value is 0, and at x equals 3, the function value is a cube root of 9. So the cube root of 9 is the largest value. That's our absolute maximum that occurs at x equals 3. Smallest value I see on at those 3 points is 0. The absolute minimum then is 0, which occurs at x equals 0.